Hello scholars, today we're going to do a couple of problems that require us to interpret fractional exponents as roots. Now this can seem somewhat procedural when you get down to it, however it's all coming from sort of just an observation, right? So let's say if I'm looking at the square root of some number x, okay? Let's say that I have a hunch. I have a hunch that I should be able to write this number as x to some power. Let's call it to the a power, okay? To the a power. I don't know if I can, but let's just say I have a hunch, right? And what we can do is we can think that if this thing is equal to this thing, if these two things are in fact equal, I should be able to square each one and get the same thing, right? If they're the same, assuming they're both positive, and we'll assume that they're both positive here. And so when you square both sides, well, I know that the square root of x squared, it's sort of like doing an inverse operation. So I just end up with x equals, and I know from my power law, one of my exponent laws, that this is just equal to x to the 2a power, because I multiply them, right? So it's equal to x to the 2a power. And then I think, well, x is really just x to the first power. So x to the first power is equal to x to the 2a power. Well, that's only true. That implies that 1 equals 2a, which implies that a is in fact 1/2, right? And this is how fractional exponents are born, right? So we're saying that the square root of x, so here, I will just summarize. We're saying that the square root of x is actually equal to x to the 1/2 power. This is sort of our fundamental starting place, and from that we can build up all of these relationships, right? So the first one, x to the 1/2, is the square root of x. It turns out that the nth root of x can be written as x to the 1/n power. And it turns out that we don't just need to have, or we can't just interpret fractions with a 1 in the numerator, right? We can interpret any numbers, right? So for example, right, for this one, we could say that x to the 2/3 power is really the same thing as the cube root of x squared, okay? For example, that's one way of rewriting this law, or, right, the cube root of x, all that quantity squared, okay? So that's the interpretation of this thing, which looks very symbolic, I understand. Okay, so let's do a couple examples and then we'll see if we can really make sense of this. Okay, so for example, simplify 49 to the 1/2 power. Easy if we know that anything to the 1/2 power is the same thing as the square root of that number. So the answer is 7. Let's do another one. Simplify and write your answer using root notation. And root notation, that just means like something like this, right? Should be something like this. Some root, maybe something inside here, there's a power. Okay, so first step is I have 5 to the 6/7 power divided by 5 to the 4/7 power. I can use my exponent law. When I'm dividing, it's the same base, so I can do it, right? You got to check, make sure it's the same base. When I'm dividing, I just subtract exponents. So 6 to the 7th. So here, let's just write it all out explicitly. So this is 5 to the 6/7 minus 4/7 power, which is really just 5 to the power of 2/7, right? And now I can rewrite that as the 7th root of 5 to the squared, 5 to the 2nd power. Or if I wanted to, I could rewrite it as the 7th root of 25. And you may ask, what the heck is this number even mean, right? Well, this is the number that if you multiplied this number by itself 7 times, in other words, if you raise this number, here's the number, if you raise this number to the 7th power, means multiplied by itself 7 times, you would get 25. So that's what this value means. That's what the 7th root means. It is that number which, when you raise it to the 7th power, you get whatever's in here, in this case 25. Okay, let's take a look at a couple more examples. Express in radical form xy, quantity xy, to the negative 2/3 power. Okay, well, so first off, we take a look, and we see that this xy is in parentheses, which means the whole thing is going with us. Wherever we're taking this thing, the whole expression xy is going to come with us, right? That's different if it said x y to the negative 2/3 power. This would be a different problem, right? In this problem, the only thing that is being raised to the negative 2/3 power is y, and the x would sort of hang out, okay? But in this case, everything is going together. So let's take a look. First step, I look at this problem and I see, there is a negative exponent, and I know how to rewrite negative exponents. I rewrite them using this reciprocal power, or this reciprocal idea. So I'm going to do 1 over xy, all of it, to the positive 2/3 power, okay? And then I want to say we're asked to express it in radical form, and radical is just another word for roots, right? Like a square root, a cube root, a radical form. So I can do that. This is nothing more than 1 over the cube root of the quantity xy squared, okay? So this is the same as this. Now again, to move from a 2/3 power to the cube root of something squared, that's just the pattern, okay? That's just the pattern that we saw, right? Right here. That's this pattern right here. And if we say, well, oh my gosh, I'll never be able to memorize this, how confusing? No, spend 2 minutes, make a flashcard, memorize it, go over it for 3 nights, 2 minutes every night, 1 minute every night. It'll take you a total of less than 5 minutes and you'll have it memorized, right? And then when that question comes up on the test, you'll get it right. That's all there is to it, okay? So I told you it is a little procedural, but it's doable, it's feasible, okay. So let's take a look at one more problem. Ooh, this looks complicated. If the 5th root of 2 to the 70th power is equal to 4 to the y power, what is the value of y? Now you do not want to guess and check here, because 2 to the 70th power, you're not going to be able to get it on your calculators, much less figure out what number when multiplied by itself 5 times would give you 2 to the 70th power. It's just too much information going on here, okay? So we're going to take it step by step. First step, let's rewrite this root, this radical, using exponents. And we like that idea because once we get everything to look like exponents, we can work with it. We can use these exponent laws that we have. We can manipulate these expressions and equations. So this is the same thing as 2 to the 70th power, right? 2, well, actually, we can rewrite it. We can write it this way, actually. This is the same as 2 to the 70 over 5 power. Okay, you can double check that. The 5th root to the 70 is 2 to the 70 over 5 power. So now we have 2 to the 70 over 5 power is equal to 4 to the y power. Let's just do a little math. 70 divided by 5. 2 to the 14th power is equal to 4 to the y power. So y is equal to 14, right? There's an exponent here. There's exponent here. No, y is not equal to 14. Why not? Because you can only do this sort of pattern matching of exponents if they have the same bases, but they don't have the same bases. There's a 2 here and there's a 4 here. So let's get them to have the same bases, okay? So let's keep the 2, right? We want to keep the smallest base. So I can say that 2 to the 14th power is equal to, well, 4 is nothing more than 2 squared, right? Now we got the same bases. So this whole thing is 2 squared to the y power. And again, I can use my power law, my exponent law. This is nothing more than 2 to the 2y power. So let's just do it all in red now. I have 2 to the 2y power is equal to 2 to the 14th power. Now, if we want to deal, now we can say, okay, so 14 and 2y, these things have to be equal to each other because we have the same bases, right? That's what allows us to do this. We have the same bases here. So we end up with 14 equals 2y, otherwise known as y is equal to 7. So this looks like a complicated problem, but again, what are our steps? Step 1, rewrite the root as an exponent form so we can manipulate it, so we can do algebra with it. Step 2, make sure that the bases are the same bases. If we have the same bases, then we can work. And then the rest is just pattern matching, right? Matching the values of the exponents. Have a great week.